I'm Don Machholz, and you're listening to Looking Up with Don. This is the Looking Up with Don podcast, episode number 73 for the week of May 26, 2021. The related website for this podcast is donmachholz.com. That is spelled DONMACHHOLZ.com. 2 H's. What's up in the sky this week? As our week begins on Wednesday, May 26, the moon is having a total lunar eclipse. A nice way to start the week. During the rest of the week, the moon rises nearly an hour later each night, and by this weekend will be rising about midnight, giving us a couple of hours of dark sky before moonrise. This also gives us the opportunity to observe and image the rising moon. 2 events I have always been impressed by and never tire of watching: the moonrise over a distant horizon and the dimming of satellites as they enter the Earth's shadow. Early this week, on Friday, May 28th, the planets Venus and Mercury will be remarkably close together in the evening sky. This is a conjunction, 2 planets close together. To see them well, you need a low horizon in the direction of the west-northwest, and you need to get outside less than an hour after sunset, as they'll be only 17 degrees from the sun. The motion of each planet in relation to the background stars is this. Venus is moving up at about 1.2 degrees per day, while Mercury makes a southward motion before heading back down towards the horizon. In relation to the horizon each night, Venus moves up a fraction of a degree each night, while Mercury is slowly sinking back to the horizon. At their closest on the evening of May 28th, 29th, they will be only 1/2 degree apart. This can be separated by the unaided eye and should look great in binoculars and a telescope. Mercury will be much, much fainter than Venus. For the Western Hemisphere, North America and South America, the evening of Friday, May 28th is the best night, as they will be at their closest. For the Eastern Hemisphere, both the evenings of Friday, May 28th and Saturday, May 29th will find them close to each other. M1, the Crab Nebula, will be close to both, 2 degrees south of Venus on May 28th, but being only 17 degrees from the sun, well, you get extra points if you can pick up the Crab Nebula this close to the sun and this close to the horizon. Over the next few weeks, Mercury will slip back into our horizon and pass south of the sun on June 12th in less than 2 weeks, while the planet Venus will become the bright, dominant object in the evening sky through the end of this year. Will you be able to see the International Space Station this week, which for our purposes begins Wednesday, May 26th through Tuesday, June 1st? Well, it all depends upon your location. And this week we have 6 zones. All you need to know is your latitude. North of 56 degrees north, you will not see it at all. From 30 degrees through 56 degrees north, the International Space Station will be in your evening sky for part or all of this week. At the north end of this band, 53 through 56 degrees north, it will be visible only in the first few days of the week, then it will disappear. South of about 48 degrees north, the ISS will be in your evening sky all week long. From 25 through 30 degrees, a rather narrow band, The ISS will start becoming visible in your evening sky around midweek. Now for a big area from 33 degrees south through 25 degrees north, the ISS will not be visible at all this week. Further south, between 38 and 33 degrees south, the ISS will be visible, but only for the first couple days of the week in your morning sky. South of 38 degrees south down to 55 degrees south, the ISS will be in your morning sky all week long, sometimes twice per night. To determine where it will be in your sky, go to the website heavens-above.com and enter your location, then click on ISS. As for comet observing this week, the moon is bright in the morning sky. Next week, we'll discuss a morning sky comet as the moon dims there. Comet 2020 R4 Atlas, which we have been following for the last few weeks, has now dimmed in our evening sky. Now for the astro class. When I was teaching the adult education class on astronomy in Sierra College in Northern California, this was a continuing education class, no tests, no grades, no credit. I initially did not discuss the sky's coordinate system. I figured it was too complicated, and the students don't really need to know that if they're going out to look at the brightest and best objects in the sky. But what if they wanted to take the next step to find and observe the fainter objects? What if they want to communicate the location of something to someone else? So I began teaching the sky's coordinate system, and no, it was not complex. And it gave the students the ability to go far beyond the boundaries of the stuff I was teaching in the classroom. I've been working on a project lately in which I've had to transfer positions on my hand-drawn maps into a coordinate system that can be used by astronomers to locate the same object in the sky. 40 years ago, I was doing the opposite, plotting hundreds of objects onto my new star maps based upon their coordinates. Yes, it's a good idea to understand this concept. That coordinate system is similar to the longitude and latitude system we have for locations on the Earth. It is a two-dimensional system. It does not tell you how far away an object happens to be, just where it can be found on the sphere of the sky. And for objects close to the Earth, the coordinates will be slightly different depending upon from where on Earth one is observing it. On Earth, longitude is the direction east or west from a specific point on the Earth's surface. In the sky, it is called right ascension, and it is measured eastward from a specific point called the first point of Aries. A measurement in degrees seems logical, with 360 degrees to go around the whole sky. But an even better idea is to measure it in hours and minutes. At the equator, 15 degrees is 1 hour of right ascension. Those of you quick with math have already figured out that 24 hours times 15 degrees equals 360 degrees. How long does it take for 1 hour of right ascension to advance 15 degrees? Answer, 1 hour. Astronomers are quite comfortable using this nomenclature to define where something is in the sky. For instance, an object may be at 06 hours, 45 minutes, 08 seconds, which is often written as 06H space 45M space 08S. Even shorter hand is 06 space 45 space 08. the jargon of astronomers. Now, for a fact that you will probably not use in your everyday life, but it is important anyway. I wish this were not true, but it is a necessary evil if we wish to keep up with the times, so to speak. That starting point, the first point of Aries, slowly moves. Something like changing the goalpost. But it does move slowly, taking 26,000 years to go all around the sky once. This is because of precession. The Earth spins on its axis each day, tilted 23.5 degrees, and it also has a slow wobble, taking 26,000 years to make one complete rotation. During those 26,000 years, the poles of the Earth, that is, the axis on which it spins, makes a circle spanning 23.5 times 2, which is 47 degrees in diameter. Presently, that axis in the northern sky points to the North Star, known as Polaris. But give it a few thousand years and Polaris will no longer be the North Star as the Earth has drifted away to some other part of the sky. Over the centuries, this adds up. The first point of Aries, which used to be in the constellation Aries, is now in the next constellation over, Pisces. But we still call it the first point of Aries. This is when the sun, on its path around the sky, crosses the equator going north. That's what shifts very slightly every year. In your lifetime and in my lifetime, this is a small adjustment. Objects will change by less than a degree in the course of your lifetime. Quite often in astronomy circles, we either state the reference time for the first point of Aries or assume it to be more or less the present time. This is known as the equinox. In the mid-1900s and until about 1985 or 1990, the equinox universally used was 1950. Coordinates were calculated using the first point of Aries, where it was located in 1950. When I was younger, everyone was using the 1950 equinox. In the late 1900s, we switched over to equinox 2000. That's where we are now, and we'll be there for a couple more decades. I once owned a 2010 Equinox, but now we're talking about motorized vehicles. Let's get back to the sky's equinox, which travels much more slowly and lasts longer. When the equinox changes, the coordinates of fixed objects change slightly. They have not moved in the sky, just the coordinate grid overlay has moved a bit. Some 250 years ago, Charles Messier was careful to measure the positions of galaxies, clusters, and nebula that he observed. Well, they are not in those same positions now. They are in the same place in the sky, but the numerical grid coordinate system now has a different number to identify that location. He was probably using Equinox 1750, so the numbers he came up with back then have to be recalculated to match our present coordinates if we want to point to them today. Now, this can be done with a calculator or a computer program. It's not difficult. Just remember it has to be done when you switch equinoxes. But as I said, everyone is now using Equinox 2000, so at least we are all on the same page. So that is right ascension, the longitude of the sky. What about the latitude of the sky? Well, it's called declination. Declination is measured from the equator to the north and from the equator to the south. When you head north, the numbers begin at 0 and go to 90. When you head south, they start at 0 at the equator and go to -90. Declination is measured in degrees with fractions of a degree, which are minutes and seconds. For instance, minus 16 degrees, 43 minutes, and 24 seconds. Sometimes this is written minus 16 with a degree sign, 43 with an apostrophe sign for minutes, then 24 with a quote sign for seconds. For typing the degree symbol, there's a couple of ways to do so. I hold down my Alt key while I type 0176. That will give you the degree symbol. Put together, the right ascension, which was 06 hours, 45 minutes, 8 seconds, and the one I just gave for declination, and we're all looking at the same object, the star Sirius. Just as the right ascension changes over the years due to precession, so does the declination change. Learn and understand the concept of right ascension and declination. This week's evening and morning star maps, Podcast 73, Maps 1 and 2, show the grid lines for right ascension and declination. Next week, I will discuss light pollution. This week, let's learn the constellation Hercules. It is in the northern sky, and as the night darkens this time of the year, this constellation is about halfway up in the northeast sky. It is outlined on Podcast 73, Map 3. Hercules is not a very bright constellation, but it does have one feature that stands out. That is called the Keystone of Hercules, 4 stars, and, well, it's in the shape of the constellation Corvus. And the keystone is in the center of Hercules. From each of these stars stems a branch of stars going to outlying regions. The constellation Hercules is in a transition zone, not exactly in the Milky Way, and not really in our galaxy-rich part of the sky. It has 2 bright globular clusters. One is M13, cataloged as the 13th object in Charles Messier's catalog. This is one of the brightest globular clusters in the sky and has become known as the Hercules star cluster, or the Great Hercules cluster. The other globular cluster is M92. M13 can be seen with the unaided eye. It appears as a faint spot, almost no diameter to it, although it might appear as a faint fuzzy star, because we're looking at it with no magnification. Hercules is usually depicted as upside down in the northern hemisphere. His head is to the south and his legs are to the north. Seen from the southern hemisphere, Hercules does not get very high in the sky, but at least he's not upside down. So get to learn the constellation Hercules. With binoculars, let's look at M13 and M92. Both are identified on Podcast 73, Map 3. M13 is magnitude 6.2 and measures 13 arc minutes in diameter, nearly half the size of the full moon. It has hundreds of thousands of stars. Finding M92 is more challenging. It's fainter at magnitude 6.9 and is slightly smaller, 8 arc minutes in size. But under almost all sky conditions, it should be visible in binoculars. Compare and contrast M92 with M13. They're about the same distance from us, 25,000 light years, but one is physically larger than the other. Through the telescope, M13 is spectacular, with many of the outer stars resolved. Generally, with globular clusters, I've learned this over the years, the larger the aperture of your telescope, the better the view. Look for the propeller made up of 3 dark lanes on the southeast edge of the cluster. M92 does not resolve quite as well in a telescope. It appears compact, while M13 is more spread out. To recap the podcast, what's up this coming week? Mercury and Venus on Friday evening, low in the western sky. And get to know Hercules with its two globular clusters, M13 and M92. You have been listening to Looking Up with Don, podcast episode number 73 for May 26, 2021. I'm Don Machholz. Once again, the related website for this podcast is donmachholz.com. That is spelled DONMACHHOLZ.com, 2 H's. You can contact me at dontheastronomer@gmail.com. Once again, dontheastronomer@gmail.com. God willing and pod willing, I'll be back next week for another episode of Looking Up with Don. We will discuss what's up in the sky and discuss light pollution and what you can do about it. All that and more. Thank you for listening. See the sky this week. I'll see you next week.